All right, so you've memorized the reactions, and now you're applying them in these one-step synthesis problems. So as you look at this, you would see that you have an alkene, and that you have two steps. One with borane, the BH3, and tetrahydrofuran, that's the THF. And then in the second step, hydrogen peroxide and sodium hydroxide. And so because you know these reactions, because you've taken the time to memorize them, now when you see that, you recognize that that is hydroboration-oxidation. And so in order to apply that reaction to this specific alkene to predict the product, you'll need to know three things that happen in hydroboration-oxidation. What do you add, where do you add it, and how do you add it? So what you add in hydroboration-oxidation is hydrogen and OH. So essentially water across the double bond. Where you add it is crucially anti-Markovnikov. So anti-Markovnikov means that hydrogen goes the place where you would not expect it in a Markovnikov addition. In other words, hydrogen goes to the more substituted carbon. And there's no rearrangement. The only reactions that have rearrangement in this chapter are hydrohalogenation and acid catalyzed hydration. So no rearrangement. And then the other thing that you'll want to know is that this adds syn. Syn means that the two things you're adding, in this case the H and the OH, are going to add on the same side of the double bond. So syn, same side of double bond, the H and the OH. Now that'll kind of only matter if you have a branch on both of those. So you'll want to make sure that the branch switches. And we'll see an example of that. We might see an example of that in we will in the next example. The other thing you want to think about with how is the chiral center again. So if you have a chiral center, you're going to get a racemic mixture of the two enantiomers. So that's going to be a 50-50 mixture of the R and the S enantiomers. And that's happening because these double bonds are flat, and so this reaction can happen with equal likelihood on either side of that double bond. When it happens on one side, you'll get an R. When it happens on the other side, you'll get an S if you form a chiral center. And of course, if you don't form a chiral center, then it's just not applicable. You don't have to worry about that. So not applicable. Okay, so knowing that, we'll take this molecule and we'll look at the two carbons in the double bond. Because there's no rearrangement, the two things we're adding will add onto the two carbons that are in the double bond. So the first thing we're going to add is hydrogen. Hydrogen is going to go, because this is anti-Markovnikov, hydrogen is going to go to the more substituted carbon. So on the top we have a primary carbon, on the bottom we have a secondary carbon. Hydrogen is going to go on the more substituted carbon in this example, in this reaction, because it is anti-Markovnikov. And so we're going to erase those pi electrons. Those are the electrons that we are going to use to hold that hydrogen on to the carbon chain. And because that's where the hydrogen goes, that only leaves us one place for where the other group, the OH, is going to go. It's going to go on the less substituted carbon. Now, both of these groups would add syn, but there is no chiral center here, and so it kind of doesn't make a difference what direction they're pointing in. Well, the bond just has to rotate, and as it does, the molecule everything can change position so that you don't have a chiral center anywhere. So you don't have a chiral center on this molecule, so this is you can stop here. You don't have to worry about the syn addition. That's if you have chiral centers or rings. Again, we don't have that here. So in this case, you can just leave this as your product. And ideally, as you practice with this, you can get rid of that H. It's there, it's just implied. And so that would be the product for this particular reaction. So knowing that about this reaction, let's try to do this on a different carbon chain. And you'll see this, you'll see you have an alkene, and then in the reagents you have borane with tetrahydrofuran in a first step, and then in a second step you have hydrogen peroxide and sodium hydroxide. And so you'd say, oh, that's hydroboration-oxidation, and it comes with this baggage, this what, where, and how. So you'll take your molecule that you're doing the reaction on, look at those two carbons in the double bond. In this case, one is tertiary, one is secondary. And because this is anti-Markovnikov, the hydrogen is going to go to the more substituted carbon. So we'll have the hydrogen on this tertiary position because it is anti-Markovnikov. We're going to use the pi electrons to stick that hydrogen there so that that pi bond isn't going to be there anymore. And then the other group has only one place to go because there's no rearrangement. It will go on the less substituted carbon. Okay, so much for what and where. Now how? In this case, we have a ring and we have two chiral centers. And because of that, we have to make sure that these two groups, the hydrogen and the OH, are adding on the same side of the double bond. So they'll either both be coming out at us, and notice, because they're both coming out at us, they're syn on the same side of the ring or the double bond, or they're both going away from us. Now, because these carbons are all tetrahedral, if you do have this hydrogen, for example, coming out at you, then that means that another bond is going to be going away. You could technically choose whichever bond you want to be going away, right? Because in tetrahedral carbons, you'll always have two bonds in the plane, one coming out at you and one going away. The easiest one to have going away would be the methyl group. And so I'll switch that methyl group so that it's going away. On the other hand, if the hydrogen is going away, then that means that this methyl group would be coming out at us to give us that tetrahedral shape, where you have two bonds in the plane, one coming out at you and one going away. So these would be completely acceptable structures. You'd get both of these as your product here. Notice you've added the hydrogen and the OH syn. Notice it is the hydrogen and the OH that are syn. It is not the methyl group and the OH that are syn. It's the hydrogen and the OH that are syn. And one thing you might see, as you get better at this and you start erasing the hydrogens at the end, they're still there, they're just implied on these skeletal structures. One thing you might see is that if the untrained eye looked at this, they might say, wait a second, that's not syn. The OH is coming out at us and the methyl group's going away. Except what is syn are the things you added, right? The OH and the H. The H is just implied. And so likewise, you would see that with the other one. So that's a common source of confusion, is thinking that the branch will be the same as the OH. No, it's the H that's pointing in the same direction as the OH. And you get a 50-50 mixture of those two enantiomers. So those are a couple examples of how you might approach a one-step synthesis for hydroboration oxidation where they give you all the reagents.